Now let us look at one very popular example for deadlocks that are studied in or that you will find basically in almost all uh, operating system books, which is the dining philosophers, renamed by some authors to the dining lawyer's problem, where you have number of philosophers, n philosophers, in this case let's say 5, and between each pair of philosophers there is a single fork, and thus there is a total of 5 forks between them. The philosophers each have basically time to think about the philosophy of life, and during that time they do not need any forks. And there are times where they eat, and in order to eat, a philosopher needs 2 forks, both the one on their left and the one on their right. The contention for these forks and the synchronization problem that ensue are what makes this problem we study in concrete programming. So let's look at this example. So you basically have P1 philosopher 0, philosopher 1, philosopher 2, philosopher 3, philosopher 4. If you look at the thing, I mean, while they're thinking, it's fine. There are no resources on which they are going to fight. When you call get forks, suppose that each philosopher picks the right fork first, the fork on his right hand first, or the fork on his left hand first, okay, and then picks the left one. So P0 will pick fork 1, P1 will pick fork 2, P2 will pick fork 3, P3 will pick fork 4, and P4 will pick fork 0. Okay, now they all try to pick their left hand forks. Well, unfortunately, there are no left hand forks for any of them. So they will all starve to death. Okay, and they all cannot eat. So this is basically the problem with the dining philosophers problem. You basically have a deadlock once everybody picks a fork on his right hand side or in his left hand side. So for example, the get forks routine here picks the left hand one first and picks the right hand one next. Okay, that means that you can end up in infinitely waiting for a fork on your other side. This brings us, I mean, the textbook has some solution, but this brings us to common concurrency problems and how to handle common concurrency bugs. Now, let us talk about a study that was done on 4 major and important open source projects: MySQL, Apache web servers, Mozilla, the web browser, and OpenOffice. So these are very large projects, open source, that some people thought, let us study them, and let us check what sorts of concurrent programming problems are there in their code. And basically, in the study, they found that although these are basically developed by highly skilled engineers, they still they still could see that there are multiple bugs in their code bases. Okay, and these are very mature code bases. These are code bases that have been developed by really skilled people. So MySQL, which is almost the backbone of almost half of the internet. I mean, it's very, very popular now. Now not as popular as it was, but it is a very popular database server system. So the authors of that study could find that there are 9 deadlock concurrency issues in MySQL and 14 concurrency bugs, but not deadlock related. So maybe race conditions or other sorts of bugs. The Apache web server was not was much better on the deadlock side. Okay, but it had almost the same number of non-deadlock concurrency issues. Mozilla had a stunning 16 deadlock bugs and 41 non-deadlock bugs. And if you look at that, I mean, given the number of, I mean, these might sound like very few bugs in such a large code base, but given the number of people who are actually using these softwares, I mean, you are eventually going, one of us is eventually going to hit one of these and will have to restart his system. OpenOffice, I mean, was much better because OpenOffice, it's basically like Microsoft Word and Microsoft Excel and so on. There were much fewer deadlock and non-deadlock bugs into it, and this is what these authors could find. So non-deadlock bugs make up a majority of concurrency bugs. So let us look at what are these, how do they arise, and how can we fix them. So the first type of problem encountered is referred to as an atomicity violation. Here is a simple example found in MySQL. Okay, in this example, the two different threads access the field proc info in the structure thread. Okay, so basically you have thread 1 accessing proc info and thread 2 changing proc info. Okay, actually both of them are changing it, one of them using fputs and one of them setting it to null. Okay, the first thread checks if the value is non-null first and then prints its value. Okay, the second thread sets it to null. So the issue now is that when the first thread resumes, if you have basically, if the first thread jumps, basically checks if it's null and then tries to print it, okay, then the scheduler basically schedules the second thread sets it to null, okay, then the first thread continues to run, it will actually have a null pointer different referenced by fputs, and that will basically blow up your MySQL. So based on what you know, what would be a fix to this?